Okay, so remember last time we were talking about rotation, right? And we defined our new coordinates. Theta, right? And we tried to map everything we could from our understanding of linear motion to rotational motion, right? And we did things like we defined a new velocity, right? And we defined a new acceleration. And then we wrote all the kinematic equations, which are very similar to the translational kinematic equations. You just replace one variable for another. All right, so that was very helpful. Today we're going to talk about force. Okay, rotational force. Okay, rotational force we essentially call torque. Okay, so why do we need a concept of rotational force? Why do we need to define rotational force?
Because we have a rotational acceleration.
Okay, so we have rotational acceleration, and therefore
we need something to be able to change that acceleration.
okay, or we observe that there is acceleration in the world, and we wonder, how do we describe it, right? Another comment?
So I was just going to say we're probably not acting as if everything's pushing on the center of mass anymore.
That's right, yeah, we see rotation in the world, and we're going to have to do some calculations, like if you apply this amount of force to this object, how quickly does it rotate? All right, so we need to be able to relate this to this acceleration to force. And so we need a concept of rotational force. Okay? Now rotational force is a little bit trickier than linear force, right? In the same way that, remember, we also defined this is our moment of inertia. Yeah, inertia. And how is the moment of inertia different than mass? What is the critical difference here? Yeah, it depends on where you calculate it, right? You have an object, if it's not, yeah, no, that works. You have an object, like a sphere, it has one moment of inertia around this axis, a different moment of inertia around this axis, right? It'll rotate differently if you push it around one axis or another axis. The same thing will be true for force. All right, imagine you have some nut you're trying to turn, right? And you have your wrench, right? If you apply a certain force here, it's not going to turn the nut as much as if you apply the same force at a different radius, right? That's why we have these wrenches, right? That's the whole idea, right? To be able to apply a force with a longer lever arm. So the key here is the distance between the point of rotation and where the force is applied, called the lever arm. Okay, so we need to build into our concept of rotational force the fact that it's more effective if you have a longer lever arm. Okay, so let's think about that a little bit more generally. I mean, say you have some weird object, an egg or something, I don't know, and you're going to rotate your yolk, right? You're going to rotate it around the yolk, right? Take your egg, you put a pin in it or something. Now what happens if you apply a force like this? Is it going to rotate? Why isn't it going to rotate? I'm applying a force. The force is applied at a point which is different, which is pretty far away from the axis of rotation. Why am I not going to get any rotation here? No component of the force is along the direction of rotation. Well, I haven't defined the direction of rotation, right? I just defined an axis and put a force on it.
The force is parallel to the lever arm?
The force is parallel to the lever arm. Well, let's think about what the lever arm is, right? So that's exactly the right idea. One way you could think about it is say, well, here's the lever arm, right? It's like this. I draw it from the point of rotation to the place I'm putting the force, and he's exactly right. The force is parallel to the lever arm. Here, the force is perpendicular to the lever arm. That's why it was effective. If I had drawn a force like this, I wouldn't be turning the screw, would I? Right? So this case, so now we've learned if the force is parallel to the lever arm, you don't get any action. Another way to think about it is to extend the line of action of the force. Okay? Say, well, I'm going to draw a dotted line through where the force goes. Okay? And then I'm going to take the lever arm to be the distance from the axis of rotation to this line of action, which in this case would be 0, right? So it's just two different ways to think about the same concept. I'm not trying to teach you two concepts, just one concept from two different perspectives. One is calculate the lever arm draw the lever arm from the point of origin to the point where the force is applied, right? And there you have a non-zero lever arm, but you have an angle. You have no angle between these two, so it disappears. And we'll talk about the mathematical formulation in a moment. Or extend the line of action as close as you can to the point of rotation and look for the lever arm, and there you see it's 0. So if instead you apply your force here, for example, right, then you can either draw a line of action of the force and say, aha, I have a non-zero lever arm and a non-zero force, and as your intuition suggests, this will give you a rotation of your egg, right? Or similarly, if you applied a force like this, right, up here also, you could extend the line of action and then calculate the lever arm. Okay? Now, in this case, we call the lever arm L. If these two things are perpendicular, as you extend the line of action so that the force and the lever arm are perpendicular, then we can write the torque as the magnitude of the torque as the magnitude of the force times the lever arm. Okay, in this case, when the force and the lever arm are perpendicular to each other. Okay? Now, to talk about the more general mathematical form for torque that you can use for any angle of lever arm and force, for example, if you wanted to draw the lever arm like this and then calculate the torque, then we need to just think for a moment about the cross product. And I'm 95% sure that everybody here knows how to do a cross product, but just in case, let's just review it briefly so that we're all talking the same language. Some of you might know this as the inner product. But in general, so we're stepping now into a mathematical universe outside of physics. If you have a vector A and a vector B, okay, and you want to calculate their cross product, then the cross product is perpendicular to both. Okay, this is C, is A cross B. All right? Sometimes people call this the outer product, to contrast it with the dot product, we sometimes call the inner product. Interesting things about the cross product is that you get a vector. Remember, a dot product, A dot B, you get a number, it's a scalar, just a value, it doesn't have a direction. This has a magnitude, right, and a direction, and the direction is perpendicular to both. So A and B, two vectors are enough to define a plane, and the cross product is perpendicular to that plane. Okay, and the magnitude of C is the magnitude of A, magnitude of B, times sine of the angle between them. Right, and you remember for the dot product, we had the cosine here. Here it's the sine. So what does that mean? It means that you only get non-zero values. Did I get that wrong? What's that? Oh. You only get non-zero values if these two things are, yeah, that's right, sorry. So if these two things are parallel to each other, you get 0, right? So for example, A, right, they're parallel to each other. A cross A magnitude is equal to 0 because the angle between them is 0. So you get the maximum value when there's a 90-degree angle between your two vectors. okay, when they're already orthogonal. Okay? Questions about cross product? That totally review for everybody? Yeah? Okay. So let's come back and think about and use cross product to help us to define a more general concept of torque. Okay? So let's take a concrete example. All right, you have some lever, literally a lever with an arm on it. Okay? And you apply a force up like this. Okay, and so this is some angle phi. So one thing you could do is say, and this is a vector of length r. So one thing you can do is say, well, the lever arm here is r sine phi. Okay, so torque, the magnitude of the torque is the magnitude of F times r sine phi, right? I've extended the line of action of from the point here to get the minimum lever arm, and I found that it's r sine phi because it's just this component of the triangle, and the magnitude of the torque is just Fr sine phi. Okay, another thing I can do is break up this force into two components. Use another color. Don't confuse you or myself. I could break this one up into two components. I could say along the lever and perpendicular to the lever, right? This one is F sine phi, and this is F cosine phi. Now, which of these two contributions is going to give me rotation? It's this one, right? You pull on the lever really hard this way or push on it that way, it's not going to turn it. So this is the only one that gives me rotation. So I can say that torque, so now these two things are perpendicular. The force is perpendicular to the lever arm. So I can use the complete lever arm here. I can say the magnitude of the torque is equal to F sine phi times r. Same answer, right? Nice to live in a universe where math works. Or I could say, well, I don't want to bother by taking all those shortcuts. I'm just going to have my vector and have my lever arm, which is also a vector, and I'll say that the torque is F cross r. Okay, this is the most generic formulation of the torque, regardless of the angle between the force and the lever arm. Now you can see how this easily reduces, for example, to this one. If the two are perpendicular, you just get the magnitude of this times the magnitude of this times the sine of their angle. But if they're perpendicular, the sine of their angle is just 1. You can see how, if you don't like to think about vectors and cross products, you can revert to a situation where the two angles are perpendicular, either by breaking the force into the useful component and the component that's radial, and using this 90-degree angle, or by drawing the line of action of the force down here and using this 90-degree angle. Okay? Questions?
That's like F cross R or R cross F.
Oh, thank you. It's R cross F. Thank you. And why does that matter? Why does that matter? Is A cross B the same as B cross A? No. They're opposite each other, right? This is A cross B, and this is B cross A. So thank you, yes, R cross F.
So the torque vector is in and out of the page?
That's right. In this case, the torque vector is in or out of the page, depending on the sign, yeah. So R cross F, it's out of it. It's out of the board. So you use your right hand to determine the direction of the result of the cross product. So if it's A cross B, you do you curve from A to B, and the result is that way. Here's R cross F, so it's out of the page. Okay, so let's use our clickers to just get a little bit of practice with that. Okay, so these four forces all have the same magnitude, F1, F2, F3, F4. There's the origin, the point of rotation. Which of these forces produces the greatest torque about this point? So why is it A? Aaron?
F1 is farthest from the origin and it's perpendicular.
And that matters because?
Because the torque is directly equivalent on the magnitude of the force and the distance from the origin.
Right, so let's compare them one by one. F3 and F4 have the same R, right? But F3 is perpendicular to the lever arm, while F4 is less than that. So clearly F3 is more torque than F4. What about F2? F2 is right along the lever arm, so there's going to be no torque there, right? F1 is clearly greater than F2. F3 was greater than F4. F1 has to be more torque than F3 because it's the same angle and a longer lever arm. So it's F1. Questions? All right. What about this one? Which of these four forces produces a torque about O that's directed out of the plane, so towards you? Use your right hands. Okay. All right, so some disagreement here. Why don't you discuss it with your neighbor? Vote again. From the origin to the point where it's active.
Okay.
From the rotation. So in this case, R is from here to here. Okay, everybody vote again, please. At this point, you've either been persuaded or you're unpersuadable. Okay, so consensus says D. Some holdouts say E. Who thinks it's more than one of these? Who knows how to press D? All right. Well, let's think about it. Two of these point in the same direction, right? F1 and F3. And they have the same lever arm, direction of the same lever arm. So their torque is going to be pointed in the same direction. So F1 and F3 point in the same direction. F2 is zero length torque. And F4 is going to point in the opposite direction from F1 and F3, right? So either the answer is F4 by itself, because it's the only one with unique direction, or the answer is E, more than one of these, right? So it has to be either D or E. All right, you guys already got that. So then it's just a question of the direction. So R goes from O to the point of action, right? And then F4 is down. So my right hand says it's towards you guys. Okay, so I agree it's F4, D. Disagreements? No? Okay. All right. let's do some examples, some calculations. Get used to get some practice, and then we'll do some actual problems. And then we'll talk about bicycles and stuff like that. Okay, so somebody gives you this problem. They say, if you got a wrench, right, around something. The wrench is 0.8 meters long. This angle is 19 degrees, and you put a force down here by putting your foot on it of 900 newtons. Okay? The question is, how much torque is there? Okay, well, torque is R cross F, right? So we're just interested in the magnitude of the torque. We can say this is magnitude of R, magnitude of F, times sine of theta. Okay? So I know what this is. It's 0.8 meters. I know what this is. It's 900 newtons. What about this one? What's theta? Should I use 19 degrees? No. What angle do I need? I need the angle between R, which is this one, and this guy here, right? This is my R vector. And the angle between this one is going to be, so this is 90, and this one's going to be 19, right? So this angle, phi, is what I want, is 109 degrees. Right? So this one is 109, so I get 680 Newton meters. So the units of torque are force and distance, of course. Okay, how else could we have done this one? Aaron?
Find the magnitude of force perpendicular to the wrench or...
All right, so decompose this force into this component and this component, right? And then just take the component that was actually being helpful. All right, so when this guy's stepping on the wrench, he's doing a lot of, putting a lot of force, which is not actually very helpful to rotation.
Which is the angle you're looking for sine? 'Cause
It's the angle between R and F, right? This one's R. This one's R. And this one's F, right?
okay, and you took it from the left to the one because it looks like a half circle on the board right now.
Oh, I'm sorry. I see what you mean. Yes, it's this angle. Thank you.
Would you join the angle from the line of action?
So let me back my message and redraw it. So this one's R, right? F is like this. Okay. If I extend this here, this is 90 degrees. This one is 19. I need this angle here, which is 90 plus 19. This is 109 degrees. It's the angle between R and F. Now what happens if I use this angle? Right, so this is 71 degrees, right? What if I'd done 71 degrees? Why is that? I get the same answer because the answer is the same. Well, the reason is that sine is symmetric, right? And so it doesn't really matter if you take and also because this is what you would do to get that component. Okay, anyway, you guys understand? So that's how you calculate torque. Now let's relate torque to motion, right? And to acceleration. Because that was our goal in the beginning, remember, is to understand the connection between rotational acceleration and rotational force. What is that relationship? Okay, well, if you have some object rotating around an axis, what's our object going to be today? You guys burn all your creativity in the 3-day weekend? An elephant. You say elephant every single time?
It's not me.
A zebra? Okay. So we have a zebra.
Girl on a stick.
Girl on a stick, you're disgusting. Who would even say such a thing? Man, you should talk to your psychiatrist, up your medication. Okay, here you have a zebra. Oh, I forgot this class is videotaped, so you can actually just go back and look and see that I did. Can't really deny it, can I? All right, so here's our zebra. Okay. It's a nose.
Donkey,
It's a
zebra,
nose.
mule.
Donkey, zebra, mule.
It's an animal.
Do you want to draw a better zebra? No?
Unfortunately.
Okay.
I like
All
the
right.
uniform stripes thing.
Okay, and we have so let's think about the point of rotation of some point on the zebra, okay? Which part of the zebra are we going to calculate the point of rotation about? The nose? Okay. So if here's our origin, right, we have an r vector, okay? And then we have some force, right? Somebody applies a force to this zebra. Okay, so this thing is rotating like this, right, around this axis. And there's a force applied to the zebra, right? Some force like this. Now this force is going to have components that are tangential to the rotation, right, like this, and forces that are radial, you know, that move towards the center. Right, so we can decompose into the radial and tangential components, and then this is the z component. So you have the z component, you have the radial component, and the tangential component. Okay, and since we're interested in not in the motion of the zebra up and down the spit, or its motion relative to the axis, we're interested in how fast it's rotating. It's this piece here that we're interested in, right? This tangential force on the zebra's nose. Okay? And we know something about the relationship between force and acceleration, right? So we can write down what we know. And we know something about acceleration, linear acceleration, right? This is the linear acceleration of the nose, and rotational acceleration is related by the radius, right? So now we have a relationship between the force that's been applied and the angular acceleration of the zebra's nose. All right, and so let's combine this. mr alpha, right? And here I just plug that in. Now what happens if I multiply both sides here by r? Times r is mr squared alpha, right? Now what is F times r? If the force is defined to be tangential and therefore perpendicular to the radius, then this is just the torque, right? And what is mr squared? It's the moment of inertia, right? Okay, so F equals ma for linear motion just gets translated to tau equals I alpha for rotational motion. Exactly the same concepts. Force is mass times acceleration, right? So last time we talked about identifying inertia, moment of inertia, as rotational inertia, right? Because we identified it in the kinetic energy formula as, we said kinetic energy of rotation is 1/2 I omega squared, which reminded us of 1/2 mv squared for linear motion. So my argument was let's just group everything between the 1/2 the omega squared and call that rotational inertia or moment of inertia. And here is validation that this is a sensible thing to do, because it also gives us a sensible definition for torque in terms of acceleration. Right? So the same quantity that lets us calculate kinetic energy in analogy to translational motion allows us to relate force, rotational force and rotational acceleration in exactly the same way as translational motion. Okay, and that's very handy if you want to calculate things like angular acceleration given a force. So if you have, for example, a pulley that's attached to a table, and somebody says, I'm applying a force of 9 newtons to this thing, and this is 0.06 meters, and the mass of the pulley is 50 kilograms. And somebody says, okay, if I apply this force, 9 newtons, tangent to the edge of the pulley, what is my angular acceleration? So how do you calculate alpha there? Well, the torque, alpha appears in this equation, right? So, and we know what I is for this kind of thing. We can just look it up in our book. I mean, I don't have it memorized, but it's mr squared over 2. Okay? We know r, we know m, we know 2. So if we need alpha, we just need to calculate the torque somehow. How do we calculate the torque? Well, we're given the force and the radius, and we know they're applied perpendicular. So we can just say the force times the radius is I alpha. Right? Now we know how to relate force to angular acceleration. So alpha is Fr over I, right, is Fr over mr squared over 2. One of these r's cancels. Right. And we know how to calculate that. And if somebody says, well, what's the tangential acceleration? Right, we could just remember okay, and we can do a similar thing with this kind of problem, which we see a lot. You got a pulley, you got a rope, you got a mass. This guy has radius r and mass m. This guy has mass little m. Okay, and this is some height above the water. Okay, the question is, what is the acceleration of mass m? Okay, now if this was not attached to the string, what would be the acceleration of mass m? G, right? No big deal, just due to gravity. Why is it going to be different here? Is there another force?
There's a force provided by the pulley, and that.
There's a torque provided by the pulley?
Well, reaction.
There's a force of tension on the mass, and that's also the torque, providing the force for the torque on the pulley to make the pulley spin.
It's a single system, right? The rope connects these two. So if you're going to accelerate the mass m, you also have to spin the pulley. Think about it in terms of energy. You turn the mass is the only thing with potential energy, right? You turn that potential energy into kinetic energy, it doesn't just anymore go into kinetic energy of this guy, it also goes into kinetic energy of rotation of this guy. Right? So his velocity is not going to be as great as it would be otherwise, because some of the energy is spent over here. Okay, so let's calculate it. What's the acceleration? Well, at first let's just think about this one here. Okay, so free body diagram for the pulley has, as you guys said, torque here, right? Now I could also say, well, there's gravity down, but then there's just going to be a normal force here fixing it. Neither of those two are going to be relevant anyway to its rotation. It's not moving anywhere, so I don't really have to think about those. Okay, and for the mass, my free body diagram just has tension T and G, right? So for this one, I say, well, the torque is the radius times the tension, right? The tension is what's providing the rotation. It gives me, and it's tangential, right? This is equal to I alpha, right? And I can just look up I and say is mr squared over 2, right? So this is mr squared alpha over 2. Right, so I have RT is equal to mr squared alpha over 2. So I can solve for the tension is m alpha over 2. So now I have a relationship between the tension on the string and the angular acceleration. Well, how am I going to find out what the tension on the string is? Well, I have this guy here, right, another equation. The sum of the forces here are mg minus t. What is this going to equal? Are those two equal to 0? No, because this thing is in motion, right? The sum of the forces is equal to the mass times the acceleration, right? Now I can plug in this guy here, right? I know what the tension is. Minus m alpha over 2 equals ma. Now what do I do? I have a single equation, because I've already used this one up. I know little m, I know big M. I don't know what A is. That's what I'm trying to figure out, right? It asked us, what is the acceleration of mass m? I also don't know what alpha is. So I have two unknowns in one equation.
Isn't the T supposed to be equal to NRA over 2 because it's R squared?
Ah, yes. Thank you. I've dropped an R here. No, I dropped an R.
Yeah.
This one here, RT. Oh, yeah. It's really hard to do algebra on the board here.
You should have an extra R in the
Yeah.
last equation.
This one here?
You should have an R on the right side.
Oh, I see, yes. But you're saying T m alpha R over T? I wrote alpha. This one's an alpha here. Okay, let's take a step back. I is mr squared over 2. This one's correct. Right, and then I just equate that to RT. So this one's correct. Then I just divide by R. So yeah, I should have 1 power of R there. Yes?
Yes.
Yeah.
Looks good. Okay, so, but we're back to the same problem. What do we do with this alpha and this A?
Is the tangential acceleration going to be the same as the acceleration of the mass because they're connected by the rope?
The rope has a single value of its acceleration, right? It doesn't stretch, it doesn't pull, it doesn't squish. So the tangential acceleration here is going to be equal to the acceleration of the mass, right? Which means that we can say A is equal to R alpha, right? So here's how we connect the linear and rotational motion, right? We say A and alpha are not two free parameters. They're connected to each other by the radius, right? Right, and that's where that R goes. So then I can plug that in over here, and I get mg, right? Minus m over 2, and then R alpha over there just becomes A, right, is equal to ma, and now I have an equation with a single unknown, right? G over 1 plus m over 2m. So let's think about whether this has the right dependence. Right? What happens when that looks upside down to me? So mg is equal to a times n minus m over 2. Right? Cross out the m's. An m. This should be a plus. Yeah. Okay, so that looks right. Okay, so does it make sense? Tell me why.
Well, if the little mass goes to 0, then it's not going to be pulling, like, gravity's not going to be nearly as strong on that mass, so the bottom's going to be really,
If little m becomes 0?
yeah, then the bottom's going to be really large, and then the acceleration is going to be 0. And then
If the little mass, little m goes to 0, then there's no acceleration. Is that what
Yeah.
you're saying?
So if little mass goes to 0,
This
then
becomes
the bottom of the whole equation.
Large, the acceleration goes to 0.
Yeah.
Okay.
If the big mass is large, then it's going to be a big bottom, and that's going to make the acceleration go
All
large.
right, so what happens when the pulley gets infinitely massive? This thing gets large, so the acceleration goes to 0, right? What happens if the pulley is massless? What's that? The object's in free fall. Okay? Okay, so there's an example of, that's a classical kind of problem we've been doing a lot, which is turning rotational potential energy into into kinetic energy, in this case with two components. Okay, let's do some thought experiments. So here we have a glider, mass m, so it's on a frictionless horizontal track, connected to this object M2 by a massless string, but over this pulley. Okay, the glider accelerates to the right, the object accelerates downwards, and the string rotates the pulley. What's the relationship between this tension and this tension? And mg, which is m2g, which is the force that the hanging object would fall with if it were in free fall. Okay, so this is a tricky one. Right? All right, so talk to your neighbor, vote again. All right, somebody was persuaded of E. Nobody thought E was true before, but somebody persuaded their neighbor that it was true. Nicely done, people. Okay, so first let's break this into pieces. First, let's think about M2G versus T2. Who wants to make an argument for the relationship between those two? Jake.
You know that the system's accelerating, so M2G has to be greater than T2, because that's the only thing that would provide any sort of force on the rope.
So let me ask another way. Under what circumstance could M2G be equal to T2?
If there was no acceleration.
Right, because then the net force on that mass would be 0, and there would be no acceleration of that mass, right? So T2 has to be less than M2G in order for M2 to be accelerating. How do we know M2 is accelerating? It says, somewhere I can't find it, but the object accelerates downwards, okay? So T2 definitely has to be less than M2G, okay? So that leaves us with B, C, or E, right? Okay, so vote again, B, C, or E. The C's have it, but not by much. So tell me about the relationship between T2 and T1. Is it equal to, are they equal to each other? Who thinks they're equal to each other? Aaron. You don't. Okay, who wants to make an argument that they're equal to each other?
I feel like they are just because I don't have any rankings, but I feel like it's the same string, just because it's going over a pulley shouldn't change the tension on it.
Is it the same string? I mean, you're thinking it's the same string. Yes, it's connected, but this is not a this is a spinning pulley, right? This is not a rope sliding over the pulley. It's not just a guide for the rope, right? Imagine the problem was slightly different, and here's the pulley, and we had two strings, one attached here and one attached here. Would the physics change at all? No, right? It's really, you should think of it as two different strings. Okay, so who wants to argue that they're not the same?
I think the T2 is going to be greater than T1 because some of the force from T2 is going to be used to rotate the pulley.
What does that mean, the force is used?
I mean, I guess.
Does it disappear after 5 seconds or something? I see where you're going, but formulate it precisely.
So.
Think about it this way. What happens in the limit when the wheel has infinite I? Right, this thing's made out of a neutron star or something, right? What happens?
Won't turn.
Won't turn, right? Which means there's going to be no force on T1, right?
Yeah. So T1 would be less than.
The only situation in which they're equal is when this thing doesn't rotate, right? And the rope just slips over it. Now, understanding rotation lets us solve tricky problems by separating complicated motion into two pieces, right? Remember the asteroid problem we had where we showed that the kinetic energy of the two asteroids could be written as the kinetic energy of the center of motion plus the kinetic energy relative to the center of motion. You can do the same thing here. If you have, for example, a cheerleader's baton, right? She throws it up, it spins, and moves in a, right? It's got this trajectory plus it's spinning. All right, you can think of this as, the baton just moves. This is the center of mass motion, right? Doesn't matter about its rotation. The rotation is not going to affect the motion of its center of mass. Why is that? Remember, we did this problem where you launch a cannon off the ship. Doesn't matter if it's a piano, doesn't matter if it's spinning, right? You apply force to the center of mass, that determines the motion of the center of mass. What were you going to say?
Is there no external forces in the system?
Right. There's only one external force, which is gravity, that dictates its motion. Okay? Plus the rotation, right? Rotation of this thing relative to the center of mass. Right? So this is the center of mass, right? This thing rotates relative to the center of mass. So this is complex motion. If you wanted to track, for example, one part of this thing, say, where does this guy go? Well, its trajectory would be pretty complicated. Right? It's like, wait, it's this one here. Well, if I had drawn it to spin more than once, it'd be more complicated.
Yeah.
But you get the idea. So you can write the kinetic energy here as 1/2 mv squared, where this is the center of mass, plus 1/2 I omega squared. So motion of the center of mass plus motion relative to the center of mass. Okay? So with that in mind, let's think about what happens when something rolls on a flat surface. Okay? So let's take a bicycle wheel, for example. Okay, a bicycle wheel, right? Here's the center of mass of the bicycle wheel, right? And it moves with some velocity, right? The velocity of the bike. And because we're not considering rotation here, we're just considering motion in the center of mass, every point on the wheel here has the same velocity, right? It's all just the velocity of the center of mass. VCM, 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 right? Now, that's its motion, right? this linear motion of the center of mass. And then hopefully your bicycle wheel is also rotating, right? Unless you slammed on the brakes. Now, here we have some angular velocity, right? And every point on the wheel should have the same angular velocity, right? Sorry, the wheel has a single angular velocity. Every point along the rim has the same tangential velocity, right? The same linear velocity. Okay, so let's add these guys up. Right? Now, in order for this bicycle wheel to roll smoothly, what you actually need is for this velocity here to balance this velocity. What do I mean by roll smoothly? I mean roll without slipping. Okay? If you're slipping, like on our initial problems, a box sliding along a surface, the two surfaces are moving with respect to each other. Right? Here I'm talking about rolling without any slipping. How do you roll without slipping? Well, there's no sliding at all, which means the point of contact have no relative velocities. And the motion comes from the rolling of the object along the surface rather than it sliding along the surface. So that means that this velocity and this velocity have to cancel. So you have no velocity here at the point of contact. Okay? How does that happen? Well, it happens if these two guys are equal, right? This one, right? So you just need to choose the angular velocity to be related to the center of mass, velocity to the center of mass, by the radius. In which case, this guy, there's no velocity. This one here has 2 VCM, right? This one has a velocity like this, and this one has a velocity like this, where this one has 2 components, VCM, VCM. And this one has 2 components, VCM, VCM. Okay? First time I thought about this, it took me a little while to absorb it, but a bicycle wheel is basically always falling forwards. It's not sliding at all. It's infinitesimally falling onto the next little bit of wheel, right? Or you can think about it as rotating around this point. But then the point of rotation moves. So in order to roll without slipping, you need friction. Right? This cannot happen if you don't have friction. If you had no friction, imagine you're standing on a bicycle on a perfectly frictionless surface, you spin the wheels, you're going nowhere, right? Or you don't even have to spin the wheels, somebody gives you a push, you slide without spinning the wheels. In order for this to happen, you have to have friction. You can't have this happen in a frictionless universe. Or I guess it would be very difficult to maintain the rotation at exactly the right speed. You could, in theory, I suppose, do it. If you're pedaling at just the right velocity to move the wheels. Okay, so if somebody says to you in a problem, rolling without slipping, that's what this means. It means that you can confidently relate the motion of the center of mass of the object to the tangential motion to the angular velocity of the object. Okay, rolling without slipping. So for example, you have a yo-yo. Okay, use your finger. Right? You have a yo-yo here. It starts here with 0 velocity, VCM equals 0, omega equals 0. It ends up down here after a moment when it's dropped height h, and it has some velocity of the center of mass, VCM, and it has some rotational velocity omega. The question is, what is the speed of the center of mass of the yo-yo when it's dropped a certain distance? Okay. Now, if this was just a problem of dropping an object and not spinning, it'd be easy. You turn potential energy into kinetic energy. We could take the same approach here, but remember we have two kinds of kinetic energy now. Kinetic energy of motion of the center of mass plus the rotation of the yo-yo about the center of mass, right? So we can say mgh is 1/2 mv center of mass squared plus 1/2 I omega squared, right? We would only have this problem initially if it wasn't rotating, but now we have this as well. And so we're given h and the mass, and we're asked to find v. We can look up what I is, but then we need to know omega. So this is where knowing that it doesn't slip on the rope is critical, because it lets us relate the velocity at the center of mass to omega, right? Now, we've done something like this before. We related tangential acceleration to rotational acceleration, right? Because we had an object on the surface, and that's fine. Here we're relating the motion of the center of mass to the angular velocity. This is slightly different, right? And this only happens when the object is rolling without slipping. Okay, so this is 1/2 mv squared. Here we put in what I is, which is mr squared over 2. And we replace this with velocity of the center of mass over r. All right, so we remove this from the equation because we've connected this velocity and this angular rotation by knowing that it rolls without slipping down the rope. Okay, and then it's just a little bit of algebra. The r's cancel. This is r squared, and this is r squared. This becomes mv squared over 4? Yes, 4. Right, so this is 3/4 mv squared. See, it would have been 1/2 mv squared, but we add a contribution from its rotation, which turns out to be, in this case, the dominant contribution, right? The kinetic energy of rotation is twice the kinetic energy of motion of the center of mass. I went from, I'm sorry, I got it the other way around. This is a 1/2 plus a 1/4, so the motion of the center of mass is twice the motion, the kinetic energy of rotation. Okay, and from here you can easily solve for what v squared is. Okay, let's do a couple more problems with rotation. It's a very similar problem. Here we have a lightweight string wrapped around a small hoop. Okay, if the free end of the hoop of the string is held in place and the hoop is released from rest, the string unwinds and the hoop descends. How does the tension in the string compare to the weight of the hoop? So what is the weight of the hoop? Which is mg, right? Just the force that would be applied, that's applied down by gravity. Okay, everybody click. So, what do you guys think? Let's give me an argument for one of their answers. Anyone over here?
So I think it's A.
Why is that?
Because there is no acceleration of the string due to the unwinding of the string.
Okay,
So-
but what about the hoop? Is the hoop accelerating?
Yes, but the hoop is basically rolling.
Okay,
So,
but the center mass of the hoop is accelerating.
yeah.
So what's the net force on the center mass of the hoop?
Net force on the center mass of the hoop would be the total movement downward from rotation.
Right, but the center of mass of the hoop is moving downward, so the center of mass is moving down.
Yeah.
So the sum of the forces is down, so there's
Yeah.
non-zero acceleration down, right? What are the forces on the hoop? and, right? So what do you think is the relationship between T and W? Aaron?
I think W is the magnitude T because the center of mass is moving downward, and the only forces acting on the center of mass are the tension and weight.
But it's attached to this string. Does that matter?
Nope.
Why not?
Because, well, you're taking that into account.
You're taking that into account in the tension. What do you mean?
Right, the force by the string is the tension. So, I guess, yeah, it would be.
Does it matter where it's attached? I mean, what if I attached it to the center?
Oh,
Doesn't matter. Well, you would get a different rotation, right? You get different motion. You're talking about different magnitudes. But the key to this problem is that they're telling you it's moving down. So they tell you the net force on the center of mass because they tell you it starts from rest and it moves down, right? So you don't have to worry about any of the other complicated stuff with rotation. You just need to know that there are two forces on the center of mass. Do you have a question, comment? This one is a lot less tricky than it looks. It's a trick question. It looks like a trick question. Okay? All right. How about these guys? Here you have a bunch of things rolling down. Okay, somebody's having a race. Okay, everything has the same mass, but of course different moments of inertia. And I can't remember them all, so I just wrote them down for you. Okay, there's a sphere, a loop, a cylinder of radius r, a holosphere. So the fourth one is a holosphere. And then there's a cylinder with the same mass, but a smaller radius. See, cylinder with radius over 2. The question is, in what order do they arrive at the bottom? Right? Who wins the race and who loses? Okay, how do we figure this one out? Yes.
I remember from the last problem we did with Pulley falling down due to gravity, and I noticed that we ended up having the reciprocal of, we ended up getting 3/4 and we had to take the reciprocal. So
Reciprocal of
bigger
what?
y would mean we'd get a smaller velocity.
Okay, so you're saying a larger I means a smaller velocity to the center of mass.
Yeah, so I just compared that.
So explain that to me physically. Why does that make sense? Why does a larger moment of inertia mean a smaller velocity to the center of mass?
Let's get this one.
Anybody else? In the very back.
it's harder to turn it.
It's harder to turn it, right? You have a fixed amount of potential energy because you start at a certain height. That potential energy is going to get moved into rotational energy and translational energy. The larger the moment of inertia, the larger the fraction is going to go to rotational energy. The smaller the moment of inertia, the less goes to rotational energy. What if you had something up there with 0 rotational inertia, right? And just like an infinitely thin cylinder. All of the energy would go into its motion, right? That's the fastest limit. So what you want is things with, so the thing that arrives first has the smallest moment of inertia. The thing that arrives last has the largest moment of inertia. So just looking at it physically, which one's going to have the smallest moment of inertia? They're all the same mass, so it's a question of the distance of that mass from the axis of rotation, right? So smallest moment of inertia comes from smallest r. So the thin cylinder is going to win because it has more of the mass concentrated towards close to the axis of rotation, right? After that is the sphere, right? It's got a lot of stuff very close to the center. After that is the fat cylinder. The sphere and the fat cylinder is not easy to compare intuitively. In fact, they're pretty close. One is 1/2, one is 2/5. So it's not a big difference. After that is the holosphere, which has all the mass at a certain radius, right? And then the loop. And the loop has, of course, the largest because it has all of the mass at a radius r, right? In the holosphere, some of it, the mass is at the axis of rotation, right? Some of it is actually touching the axis. For the loop, none of it is. It's the maximal moment of inertia. Or if you want to think about it mathematically, right? The kinetic energy has these two contributions, and you can write the moment of inertia of each of those objects as some coefficient times mr squared. and then plug that in, then as we were learning, the velocity is proportional to 1 over this coefficient. All right, so in this case, a larger c means a larger moment of inertia, so a smaller final velocity. All right, and then if you look at the coefficients for each of these objects, then they arrive in this order. Questions? All right, so that's all we have for today. There's a few more example problems.